First question was, can we go over some improper integrals? And so, yeah, let's talk about a couple improper integrals, and then somebody wanted to talk about like how to tell what series test to use. And so we'll kind of try to do a strategy for that. Okay, so improper integrals, there are two types of those. One is when you have infinity as one of the bounds. So like if I'm doing, say, the integral from, let's say 5 to infinity of 1 over, we'll say 3x minus 1 squared dx. So if we're doing something like that, so if there's infinity as one of the bounds or negative infinity as one of the bounds, and then, and yeah, I can get to the questions in chat as well. But okay, so if infinity is one of the bounds or negative infinity is one of the bounds, or if there's a discontinuity between the two endpoints or between the two bounds on the integral. So like this one is discontinuous, meaning 0 on the bottom in this case. So this is discontinuous at 1/3, and 1/3 is not between 5 and infinity. So we don't have to worry about that. But if it were, that's something else that could make the integral improper. So kind of the idea, if you watch those videos, the idea is that we don't really need a graph for this, but if you have 1 over 3x minus 1 squared, pretty much there's a vertical asymptote at 1/3. So I'm making this maybe a little farther to the right than it should be, but there's a vertical asymptote at 1/3, and then this thing decreases to 0 as you move to the right. And when we're going from 5 to infinity, we're talking about the area under the graph from 5 and up and forever. And so that's like an open area, which is what's weird about improper integrals. The thing is that when you go from 5 to infinity, we can't really handle that using just standard integration stuff or using the fundamental theorem of calculus, but we could do from like 5 to 100 billion or 5 to 100 billion factorial, something incredibly large. And all of those would be normal integrals. And so the idea is, okay, well, if you go from 5 to 100 billion, if that area is a certain value, and then when you go to 5 to 100 billion squared or 100 billion to the third or something even bigger than that, if that's approaching a value, then you would say, okay, this converges to a certain value. Otherwise, maybe it goes to infinity. And so that's the idea here. And so what you do is you say, okay, well, we can't really deal with infinity, but what we can do is we could say, well, we're going to go from 5 to r. And you just pick a random variable other than x, but I usually use the letter r. So we go from 5 to r of 3x minus 1 to the -2. And we want to talk about the limit as r approaches infinity. And so r is something like 100 billion or 100 billion squared or 100 billion factorial, something incredibly large. But we want to know what happens as r approaches infinity. And now r is just an actual number. And so then we can evaluate this like normal, which is why I bring it up and make it to the -2 power. This is a quick u substitution where u would equal 3x minus 1. And so we do the power rule, because u is 3x minus 1, du is 3 dx, so we get a 1/3 outside, and then it's u to the -2, so we get 1 over -1 u to the -1 when we do that antiderivative. And I'm not showing the steps on that, but does that make sense, how to do the antiderivative? Any questions on that? All right. Yeah, go ahead. If you have a question, just unmute yourself, you can ask.
Okay, so like, how did you get it to be like that? Like, I'm just curious as to the steps as to what you took.
To do the antiderivative there? Is that what you mean, Victor?
Yeah.
Okay, so yeah, I would do it like this. I would say we've got the integral of 3x minus 1 to the -2 power. Okay. And then u is 3x minus 1. So du is 3 dx. So I need to get a 3 in there for the du. And if I'm going to multiply inside by 3, I'll multiply outside by 1/3. And now I've got the integral u to the -2 du.
Okay.
And then I actually left it like that just because I was doing it in my head, but we're going to take a step to simplify it next.
I'm confused where you're getting the -1 from. Shouldn't it be -2?
Not here. So we're doing the antiderivative. So you've got u to the -2, and now you do the power rule. So you add 1 to the power.
Oh, okay.
You're good. So it's just been a while since we've done that stuff. -2 plus 1, -1. So we get 1 over -1 u to the -1.
Okay, so if it's so if it's just 1 over -1, should it just be -1 then, or do we have to write it that way?
I just wrote it out this way because that was what I was able to do in my head. We're going to take a step now to simplify this.
Okay, and like when do we have to use that, do it that sort of way, or is that just like completely? Or are there like other ways to do it?
Well, doing this antiderivative is a u substitution problem. I don't know that there's a better way to do this one, but it could technically be any type of integral that we covered on like the first 2 examples.
Okay.
Does that make sense?
I guess, yeah.
Okay. And then someone's saying, should we show these steps? On one, this straightforward, I would be okay if you were able to do this in your head. You should show some work. If it's more complicated, obviously you need to show it, but we need to be able to explain how we're getting from here to here. All right. And man, I didn't mean for chat to only be able to contact me, but now you can post questions publicly if you want to too. That's my bad. It was set to only private. All right. Any other questions to this point? All right. So now we plug in R and we plug in 5 and subtract. So we get the limit as R goes to infinity. And we get -1 over 3 times 3R minus 1 minus -1 over 3 times 14 because it's 3 times 5 minus 1. And now we got, well, we look at this, the limit as R goes to infinity of that. And so if we look at what happens as R goes to infinity, well, 3R minus 1 goes to infinity. 3 times that goes to infinity. -1 divided by infinity would go to 0. And so we get 0 plus 1 over 3 times 14 is 42. And so we get 1 over 42 here. And so this integral converges to 1 over 42. Right. Any questions on that problem? Okay, so that's how you deal with infinity as one of the bounds. If there's a discontinuity, you do it slightly differently from that, but not a whole lot. I want to move on to some other questions, but if we want to do more improper integrals toward the end of the review, we can do that. And then there are 2 videos where I work some of those out, but that's at least an example of those. The next question that I had received right before we got started was, can we go over just kind of how do you know what to do when on a series? So like, what is the technique for knowing like what test to use? And there's not a definite way to know that in every case. But this sheet, let me pull it up for you guys, gives some guidelines for that. So it's called Series Test Summary, and it's in the Unit 3 folder on our shared drive. And if you're not in my class, I don't know if you have this sheet or not, but I can get this to you right after the review. If you want to stick around, I can just email this to you if you guys give me your emails later. But anyway, this is kind of the summary of how these work. So series tests, if you've got the series sum, it doesn't have to be 0 to infinity, but something to infinity of AK. So K-term test or test for divergence is something that kind of applies in general. And so if the limit of the sequence is not 0, or if the limit of the absolute value of the sequence is not 0, in either case, the series diverges. And then we've got these basic series, geometric and p-series, and this is what happens in each of those cases. Geometric series covers every series that is an exponential function, so a number to the k. P-series is every power function, so k to a number. So a number to the k is exponential, that's geometric. And then, oops, k to a power is a p-series. My bad.
Okay. I found this on the web for PC.
Sorry, when I say Siri, sometimes Siri thinks I'm talking to her. So anyway, you've got geometric and p-series that kind of cover those. And then the more complicated series, until we get to ratio root test, for the most part, we're trying to break down into these. We're trying to compare them to simpler series. So if the series has all positive terms, you get this easier series called the comparison series, and you figure out what that does. You use a comparison test to prove that the series does the same thing that the original one does. And then if it is alternating, which means basically some negative terms, more or less alternating series is what we're talking about here, then you first test the absolute value. So you take the absolute value and you do the comparison tests, figure out what that does. If it converges, then the original converges absolutely. If it doesn't, then as long as the sequence went to 0 and it's decreasing, which is going to be the case in almost every situation, if the sequence goes to 0, then it's going to converge conditionally by the alternating series test. And so this is kind of the general format of most of the proofs. Then kind of separate from that, you've got ratio and root tests and integral tests. And these are when you start to mix up function types. And so let's kind of talk about in general the way that works. But that's, like I said, there's not a great way to answer the question to say, okay, this is when you always do this. But if you're talking about the standard problems there is a way to think about that. So if you have like the normal problems. And so when I'm talking about normal problems for series, I'm talking about if you have like all power functions over all power functions. Or all exponential functions over all exponential functions. So these are the most common examples. And maybe you would have -1 to the k times these things, but not always. Okay, so if you have -1 to the k times those things, it makes it alternating. And so if you have a problem like this, where I've got the sum k equals, say, 1 to infinity of -1 to the k, k squared over k to the 5th plus 6k minus 2. So if you have something like that, this is where you have -1 to the k times all power functions over all power functions. Power functions, I mean k raised to a power. So k to the 2nd, k to the 5th, k to the 1st, k to the 0. Those are all power functions. Exponential functions are if I had 2 to the k and 5 to the k instead of k squared and k to the 5th. So a lot of the standard problems work like this. Not every problem, but these are what I mean by like the normal problems. And so if you have that and it is alternating, you kind of do these in 3 stages. You do them in 3 parts. And that sheet, kind of the top 3/4 of that sheet covers this in the 3 different things that you do. You start by comparing to or considering the absolute value. And so like the absolute value here would be k squared over k to the 5th plus 6k minus 2. And then you're going to compare that to the biggest thing over the biggest thing. So if I have k squared over k to the 5th in this case, so the biggest term on top, biggest term on the bottom, and then you simplify that. And so you get 1 over k to the 3rd. And so on these standard problems, you're going to have 3 parts to this kind of proof. And so you've got this problem on the right. And in general, this is going to be a P series or a geometric series. Or it's going to be weird. And so what I mean by that is like on this problem, this one's a P series. So this one converges, we would say that first. So this converges because it's a P series where P is 3, which is bigger than 1. Now, the 1 over here is not always going to converge, but in this case it does. If this was 1 over k to the first, it would diverge. If it was 1 over k to the 1/2, it would diverge. P series is going to do whatever it does. Geometric series, if you have 2/3 to the k, that's going to converge. If you have 5/4 to the k, that's going to diverge. Weird is when you get like a constant or you get a k on the top. So like when I'm talking about that, I'm talking about like if you get 3k squared over 5k squared at this stage, instead of k squared over k to the 5th, if you get that and you get 3/5, then what that means is it's probably going to be the k-term test or the test for divergence, meaning the limit of the absolute value of the sequence is not 0 and the whole series diverges because of that. So that's if everything cancels or if the k ends up on top. So like if you had k to the 5th over k squared. Does that make sense to everybody, what I'm talking about? So in those weird cases, it's going to be the k-term test or the test for divergence. In these two cases, you're either going to get that it converges or diverges. This one either converges or diverges depending on whether it's a P series or a geometric, depending on those rules. Now, when you go back to the middle, this one will do the same. This does the same as the one over there, meaning if this one converges, the one in the middle converges. If this one diverges, the one in the middle diverges. That is 100% the case for what I'm describing as normal problems, where you have the all power functions or all exponential functions. These will do the same thing by one of the comparison tests. So you're going to use either the direct comparison or the limit comparison. It doesn't matter. Depending on what's going on, you may have to use one of the two, but as far as the conclusion, it doesn't matter which one you're using. The conclusion for this is going to be the same as the conclusion for this. If this converges, then this converges. If this diverges, then this diverges. Does that make sense to everybody? Everybody clear? So when you have these three steps, it's either going to be converge over here and converge here, or diverge over here and diverge here. Now, if it's not the weird ones where it's not k-term test, then the one over here is going to converge no matter what in both of these two cases. And so if these two converge, if we're in this first case, okay, where the one over here converges and the middle one converges, then this one converges absolutely by the absolute convergence theorem. And that sounds like you're saying the same thing twice, but the name of the theorem is the absolute convergence theorem, and what it does is called converges absolutely. And so what the absolute convergence theorem says is that if the absolute value converges, then the original series converges. So like in this case, this converges. We need to use a comparison test to show that this converges. Because the absolute value converged, then so does this one. So then it converges absolutely by the absolute convergence theorem. If these two diverge, then this is going to converge conditionally by the alternating series test. Remember that the alternating series test has three conditions. It says that the non-alternating part, meaning the part without the -1 to the k, that has to be positive, which it's going to be on normal problems. It has to be decreasing, and the limit of it has to be 0. Well, if it's a normal type of problem, if the limit is 0, then it's going to be decreasing. If the limit's not 0, that's one of the weird ones, which is the standalone k-term test. When that happens, if it's k-term test, then all three diverge, but you don't need to show all three parts. You just need to show the limit of the absolute value. This is not 0. And then that means that and then that means that it diverges. All right, does that make sense to everybody? And the person who asked that before class, do we understand kind of what I mean by that as far as how to tell? And maybe we'll look at some and talk about that.
So can I ask a question?
Sure, go ahead. Yeah.
Okay, so we can use this sort of rule as long as there's like a -1/k on the numerator.
Yes, so this is if it's alternating, right?
Okay, and like, how would we know which values to pull out for each specific one?
What do you mean, which value to pull out? Like here?
Yeah,
No,
like here and here, yeah.
The largest term as k approaches infinity. So like we know that k to the fifth is much larger than k as k goes to infinity. So you pick the biggest one.
All right.
Okay. Okay, and then somebody in chat's asking, I know there's some people asking about specific problems, and I will try to get to all those. Okay, so somebody in chat asked, why can't we use the alternating series test in the beginning? And you probably can, but you don't need to use the alternating series test if the absolute value converges. The other thing, so like in this top case, if this converges, we don't want to use the alternating series test because we know based on this that this converges anyway. An alternating series test is something that's harder to show. There's more work in that. The other thing with alternating series test is it does not tell you what the absolute value does. So most of these questions ask, does the series converge absolutely or converge conditionally or diverge? And so if you just start with the alternating series test, that would show you that this converged, but it would not tell you whether it converged conditionally or converged absolutely. Does that make sense? David's the name of the guy in chat asking that. Does that make sense? Okay, yeah, no problem. But yeah, you're right. You could start with it. The problem is you don't need to do it on these easier ones, on the ones that converge absolutely. And then here you do, but you don't want to do it until you know already the absolute value diverges. All right, and then Gavin, how do you know if it's conditional or absolute? So absolute convergence means that the series itself converges and so does its absolute value. So when you say converges absolutely, you're saying this original series converges and its absolute value converges. Converging conditionally means that the series itself does converge, but its absolute value diverges. And so when the absolute value diverges, but the original converges, that's called converging conditionally. Does that make sense? Yes, we'll go through an example now. Yep. Okay, and then the third case is they all diverge, in which case it's the K-term test. So I am going to answer Colin's questions next because it's related directly to this. I want to do an example where we talk about this. And Justin, I will post this there's a playlist on the YouTube channel called review sessions and extra help sessions or something like that. It'll be on that playlist. Okay. Yeah, no problem. Okay, so yeah, if you go into the YouTube channel, just go out to playlist, find the one that says review and extra help or something. I forget exactly what I called it, something like that. Okay, so I tell you what, so the question is, can we do one where we're actually going to do the alternating series test? Yes, but I'm going to put several series on the screen, and I want you guys to tell me which one would be this pattern where it diverges, but then converges conditionally. And so let's say we've got this series, the sum k equals 2 to infinity, -1 to the k, k over the square root of k to the fifth plus 7. And then the sum k equals 2 to infinity of, let's do k over, or well, not bad. Yeah, we can do that. K over the square root of k to the third plus 7. And then let's do the sum k equals 2 to infinity of -1 to the k. Not put a k on this one. Over the square root of 3k plus 7. Let's do that. So, so these are the ones that I mean where they're kind of normal problems where everything's a power function except maybe the alternating part. So of these three, the first one, the second one, the third one, which one has the pattern that the original one converges conditionally, but the other two both diverge? Which one's going to end up doing that?
The third one?
The third one. Yeah, so the third one's going to be like that because by the time you get over here, it's going to be 1 over k to the 1/2. So this is going to diverge, which means this middle one automatically diverges. This one converges though, because the limit of the sequence is 0. So the alternating series test is going to show us that this converges conditionally. So this is the one we're actually going to work. This one is going to be this top case where they all three converge. So it converges absolutely. The middle one is not alternating. So when they're not alternating, you're already at this middle stage. So it's either they both converge or they both diverge. There's not a possibility that you go back and converge conditionally. So this will be either converge absolutely in the middle or diverge. And that's one thing we got to watch. Once we get really good at these alternating ones, a lot of people tend to act like these are alternating and they're not. And so like when you go here, you're going to get on the right, k over k to the 3/2, which is 1 over k to the 1/2. Well, that diverges, which means this middle one is going to diverge. If it were alternating, it would converge conditionally, but this one's not alternating. So this diverges by one of the comparison tests. So this one diverges by a comparison test. This one converges absolutely by the absolute convergence theorem. And then this one is going to converge conditionally. And we're going to start working that problem. Now, what I'm saying out loud, where we're determining those answers before writing any work, that is what you want to be able to do before Thursday. That's not just because I've done series for so long, I'm good at picking it out and knowing the answer ahead of time. You should know the answer ahead of time before you really start writing the proof. This is the only thing that you focus on to determine what the answer is. That tells you the entire structure of the proof. So if you're able to pick out what that is in your head, fine. If not, that's okay. You may need to write out to get over to what this is. But once you know what this is, you should know what the rest of that proof looks like before you even start really writing anything. Okay. The third one converges conditionally. And so we're going to go through that one now. So the absolute value diverges, but then the original will converge conditionally because it's alternating and it goes to 0. So let's go through it. Let's go through this problem. Yeah, no problem. So we're doing this one. So we're going to start with the series, the sum k equals 2 to infinity, -1 to the k over the square root of 3k plus 7. And so then we're going to say, okay, consider the sum of the absolute value of ak, which is the sum 1 over the square root of 3k plus 7. And so we're going to go, okay, we're done that first. And now we're going to say, okay, we'll compare that to the sum 1 over the square root of 3k, which is 1 over the square root of 3 times the sum 1 over k to the 1/2. It's a p series. Make that legible there. Not bad. So this converges, this diverges. It's technically a constant multiple. If you don't say that, it's not a huge deal, but it's a constant multiple of a p series, where p is 1/2, which is less than 1. Now, at that stage, as soon as we knew this was 1/2, p is 1/2, we knew this diverged. We know this one then diverges. And so then this one, because it's alternating and the sequence goes to 0, this converges conditionally by the alternating series test. Now we're going to go back and show all those things, but this is the first part of the proof. Any questions to there? That's good. Okay, so now we're going to go back.
I have a question in
Sure.
regards to it. So I know with all these different rules, they have different ways of telling you which one is convergent or divergent. Like with this one, it would be if it's less than 1, it's divergent, and if it's greater than or equal to 1, it's convergent.
Greater than 1 converges, less than or equal to 1 diverges.
Okay.
On a p series.
Okay.
Okay. Yeah. All right. So now we're going to go back here, and so we use one of the comparison tests. When this one diverges over here, it goes to infinity because everything's positive. That means in order to use the direct comparison, we would like this middle one to be larger than this one. The middle one is not larger because the bottom is bigger, so that's actually smaller. So then that means we have to use the limit comparison test. So to use the limit comparison test, we say that both the series we're talking about and the easier series are positive. And we calculate the limit of the original series, or the series we're talking about, divided by the easier series, but times its reciprocal is easier for the algebra. And that limit is 1. And what the limit comparison test says is if that limit is a number that is positive, then the series here does the same thing that the series over here does. And so then this is our proof that this middle one, so the sum of the absolute value of AK, diverges by the limit comparison test. And now we're going to go back, and when the absolute value diverges, that does not directly tell you whether this one converges or diverges. If the absolute value had converged, this one converges. If it diverges, this could do either, but we know it does not converge absolutely, which is why we start with this. So now it either converges conditionally or it diverges, but if the sequence goes to 0, it's going to converge conditionally on most problems. That's what the alternating series test is saying. And so for the alternating series test, you say, okay, well, BK is the non-alternating part of the series. And so you show 3 things about BK. And if those 3 things are true, then the original series, AK, converges in that case. And so we're going to say, first, BK is positive. So 1 over the square root of 3k plus 7 is greater than 0. The second is that the limit as k goes to infinity of bk is 0. That's pretty clear here because it's 1 over infinity. And then the third thing is that bk is decreasing. That requires a little bit more work, but in this case, we can just say, okay, well, bk plus 1 is 1 over the square root of 3k plus 10. I get that because I'm plugging k plus 1 in for k. So k plus 1 goes right there. The 3 distributes, and so you get 3k plus 10. And then we're comparing that to 1 over the square root of 3k plus 7. Well, that's less than that because the denominator here is bigger than the denominator here and the numerators are the same. So this is our showing that it's decreasing. And now that means that the original series converges conditionally by the alternating series test. All right, does that make sense to everybody? Any questions on that?
When would you use direct comparison in the middle?
When the relationship that you kind of want to exist does exist. So like when the easier series diverges, we think of it as going to infinity like that, right? And so we would like this middle one to be bigger than that. The plus 7 meant it wasn't, but had this like been minus 7, then okay, this would be larger than that. So you could use the direct comparison instead. So when the easier one diverges, if this one is larger, you can use direct comparison. When the easier one converges, if this one is smaller, then you can use the direct comparison. On these like straightforward problems, not saying they're easy, but when they're these normal problems where they're all power functions or all exponential functions, you don't have to make that determination. You could just always use the limit comparison test. There are some examples where you can't, but for most problems, you could just go default to the limit comparison test. Does that answer the question?
Yeah, thank you.
Okay, yeah, no problem. Other questions on this example? And I'm looking in chat. So we don't.
Yeah, can you go over the comparison tests, like the rules for that again?
Yeah, I'm gonna try to get to everything. I'm gonna go down the chat with that. But yeah, so the idea with the comparison test is that if this easier one diverges, you want to think, okay, that means it's going to infinity. So then you want the original, or the one that you're talking about, to be bigger, because then it would have to go to infinity as well. So if this middle one was bigger than this one, then we would be able to use the direct comparison test. If this one converged, it levels off. And so then we would want this one to be smaller than this one. And so that's when you can use the direct comparison test. You don't have to use the direct comparison test. You could use the limit comparison test instead. And so, okay, so the Katie's question in chat is, so when the compared series diverges, we have to use both the alternating series test and either comparison test. Yes, unless it's the K-term test, meaning it's the weird case where you get like 3/5 over here. Does that answer the question? So yeah, no problem. But again, that applies when it's these normal ones where it's all power functions or all exponential. So, okay, I think, oh man, that's not what I wanted. The question is, okay, do we have to show all this on the exam? It depends on what you're being asked. So if you're asked to provide all the details of the proof, then yes. So like the way I design a test, and if you're in my class, you're going to get, every class is going to get 50% on WebAssign. That's the same for all classes. And then, well, I mean, it randomly generates the questions, but you get the same 50% basically. And then 50% is a written exam that's written by your specific instructor. So if you're in my class, the way I design the questions, and this is probably how most people will design the questions, some questions will say, show or prove whether the series converges absolutely, conditionally, or diverges. Show all conditions of all the tests. So on this type of problem, like 13 is almost exactly what we just did, right? And so those you would be expected to show everything. And then I have questions, and this will depend on the instructor whether they have these or not. Sorry, I was working with some people yesterday. But determine whether the series converges, absolutely converges conditionally, or diverges, circle the conclusion, and then list the test, but you don't have to show all the details. And so we were doing the details here, but like on this type of question, I would just want to know the answer and then the list of the tests you would use. And so you'd have to say like P, you would use P series here. You would use, this one converges conditionally. So you would use one of the comparison tests and you would use the alternating series test. And so like that is all you would have to list for one like this. So it just depends on what specifically you're asked. This one's already positive. And so like it converges absolutely. So you use a geometric series and you use a comparison test, but you don't use alternating series or absolute convergence because it's not alternating. Okay. Okay. I'm going to go back up to the top of the chat just to try to be fair to everybody, and I will try to get to everybody's questions. We're going to start with number 16 in the series 4 homework, just because that's the top one that I've got in the chat. Some of them were sent to me privately. Some of them were sent publicly, but number 16 on the series 4 handout, and I will try to get to everything that people are asking in the chat. All right, let me pull up series 4. And okay, so number 16 on series 4. Yeah, okay. So 16 is a relatively complicated example. And what it asks, it's show whether the series converges, conditionally, converges absolutely, or diverges. And it's the sum k equals 1 to infinity of cosine of k pi over 7 over 3k plus 2 factorial. And so, okay, there's a couple things that make this one more complicated. Cosine is what makes this one a lot more complicated as far as the structure of the proof. But the real problem with cosine is that it's not always positive and it's not always negative. So it's randomly changing from positive to negative. And when you have something like k pi over 7, it's not even like every other term is positive. It's not even like every other term's negative. It's like there's a couple positives, a couple negatives, maybe 3 more positives, maybe 2 more negatives, you know, just kind of as random. And the factorial almost always indicates ratio test, which it ultimately does, but you can't do ratio test from this cosine here. So you have to do a couple things. You have to first, we have to not deal with the negative. So we're going to consider the absolute value first. And this is one that's outside of the normal ones. And it's because of that cosine and the factorial. It doesn't fit the mold of everything else. But you start by looking at this, and you leave the absolute value bars on cosine because it isn't always positive. So it's just whatever the absolute value is, that the cosine's randomly positive, randomly negative. So there's not an easy simplification of that. But 3k plus 2 factorial is always positive. And so the absolute value of that is itself. And now, okay, the advantage of this is a series that's all positive, which means the comparison tests work. Comparison tests do not work when you're talking about ones that are randomly positive, randomly negative. Cosine, no matter how complicated the inside, is always between 1 and -1. And so the absolute value of cosine is less than 1, or it's less than or equal to 1. And so we're going to compare this to 1 over 3k plus 2 factorial. Now, we haven't proven this, but if you think about what's going on, when you talk about like p-series and stuff, remember that a p-series with like 1 over k to the 1.1 converges, and 1 over k to the 0.99 diverges. 1 over k to the first is the tipping point where that diverges, but anything bigger than that converges. The rationale as to how that can happen is that the bottom here gets bigger faster. So these get close to 0 fast enough to where the sum converges. These do not get close to 0 fast enough to where the sum converges. And that's weird to think about, that because this doesn't get to 0 quick enough, we know this diverges. These do get to 0 fast enough. So if you think logically about what's going on here, 3k plus 2 factorial, factorials grow faster than basically any other function that we've got. So they're going to grow way faster than like k to the 1.1. So if you have 1 over that, that's going to converge. So we're going to prove that, and we're going to use the ratio test to do it. But if we're thinking about, okay, what should we be doing? Well, okay, that means this converges. Well, this one's smaller than that. So this converges too, and then this converges absolutely by the absolute convergence theorem. So that's the idea here. To prove that this converges, we use the ratio test. So we're going to go through and do the ratio test relatively quickly on this. So you do the limit as k approaches infinity of the sum, I'm sorry, not the sum, of the absolute value of ak plus 1 divided by ak. And so ak plus 1 is 1 over 3k plus 5 factorial, and then times the reciprocal of ak. Now, the reason I'm getting 3k plus 5 is I'm doing 3 times k plus 1 plus 2, which is 3k plus 3 plus 2. So that's how I'm getting that 3k plus 5 factorial. But does everybody understand to there? Any questions to there? All right. And so now you simplify that by breaking down the factorials. And we can drop the absolute value because everything there is positive. But we break this down. And so we get this, and now the 3k plus 2 factorials cancel. So we get the limit as k goes to infinity of 1 over 3k plus 5, 3k plus 4.
Why don't you have a 3k plus 3 in the factorial section?
Because I just randomly skipped it, sorry. There should for sure be a 3k plus 3. And then there should be a 3k plus 3 here too. And it's still 0. Thank you. That's completely my fault. So 3k plus 5, 3k plus 4, 3k plus 3, 3k plus 2 factorial. Does that make sense to everybody? My bad. All right, limit is still 0. That's less than 1. So the series, so this one, 1 over 3k plus 2 factorial, this converges by the ratio test. Okay, so now we go back, and this middle one is positive and is less than or equal to that one. All right, so positive and it's less than or equal to that one. That means that then this one converges. By direct comparison. And now we go back over here, and now the original series, so since the sum of the absolute value of AK converges, then the sum of AK converges absolutely. By the absolute convergence theorem. Questions on that problem? That is a tricky problem. Go ahead.
Just for syntax, like on exams, are you still fine with us just referring to the original as AK? Like,
yeah.
Is that fine? Okay.
I am fine with that. If you have another instructor, you might make it clear that AK is this. But one thing I've said in my classes is I will assume if you use the symbol AK, that you mean the original, the entire original formula, unless you tell me otherwise. So if you tell me you want AK to be something else, that's fine, but you got to tell me that. I will assume AK is this. If you have another instructor and you're worried about that, just say let AK equal cosine of k pi over 7 over 3k plus 2 factorial. Like, it's completely legit if you do that, as long as you tell everybody what you're doing. I'll assume this unless my students tell me otherwise, just because we had said that a couple times in class. Other questions on this?
When you get to the comparison step,
yeah.
Can you just to the right, all the way over? Yeah, there.
Yeah.
Could you just factor out the bottom and then like not do the limit there? Not do the whole limit thing, but like break the factorial down and then multiply it and then just take the biggest term and use the P series?
No, you can't do that because this series itself, I see what you're saying. So could you in turn compare it to, no. And the reason why is because the reason this canceled out is because you're multiplying by the reciprocal. Do you see what I'm saying? So like, otherwise you've got, like, there's a lot of terms here, right? Like 3k plus 2 is approaching infinity. So like, it's not like it stops at 3k. It's like 3k plus 2. Like, let's say that k is 100 even. Then this is 302 factorial. So it's 302 times 301 times 300 times 299 times 298 times 297 and forever down until 1. And so this is the only good approach to this problem. Does that make sense, Evan?
Yeah, it does.
Okay. But yeah, I see what you're thinking, like 1 over 27k to the third here, but that's because of what happened with the ratio test. Okay. All right. Other questions on this problem? Okay. And I'm going to try to be fair and go straight down through chat to make sure I get to as many as we can get to in this time period. So number 11 on series 3 is the next one that I see in the chat. You get series 3 pulled up real quick. Okay, yeah. So number 11 on series 3. All right. So this is one where all of the terms are positive already. And we know that because as k goes to infinity, on the top, you've got 3 to the 2k plus 1, which we think of as 9 to the k, because it's 3 squared, versus 5 to the 3k minus 7. So that's 5 to the third, so 125. So the biggest term on top is 5 to the 3k minus 7. The biggest term on bottom is 4 to the 2k minus 3, because that's 16 versus 12. So if you start this like normal, you would start by saying it's like these 3-step ones up here, except you're already in the middle. You're already at one that's all positive. So you're just dealing with these right-hand 2 columns, except instead of on the right, you're not going to get a p-series, you're going to get a geometric series. And so when you do this, you would just say, okay, compare to the sum 5 to the 3k minus 7 over 4 to the 2k minus 3, and you're going to figure out that something's weird. So the algebra here is that you simplify that to be 5 to the negative third times 5 to the 3k over 4 to the negative third times 4 to the 2k.
It should be 5 to the negative 7, I think.
Yes, it should be. Thanks. My bad. Oh man, I forgot to move the eraser huge. All right, so 5 to the negative 7 right here. So then we get 5 to the negative 7 over 4 to the negative 3 times 125 over 16 to the k. So then when you see that the limit of that's not 0. And so you could scrap everything and go with the k term test, which is what I would definitely recommend doing. But you could also do it in 2 steps and say, okay, this is a divergent geometric series, and then use the limit comparison to prove that this would also diverge. And that may be what I did on the solutions just to show how to do it. But like the limit of this term as k goes to infinity is infinity, not 0. And so what I would do is then scrap this and say, okay, well, that means the limit of this original sequence as k goes to infinity is not 0. And so we do so when we're doing the limit of the sequence, you take the biggest thing on top and biggest thing on bottom. The biggest term on top is 5 to the 3k minus 7. Biggest term on bottom is 4 to the 2k minus 3. And we actually do the same thing we did in what I crossed out. And so 5 to the negative 7 over 4 to the negative 3 times 125 over 16 to the k. Well, that's infinity, which is not 0. So then the original series diverges by the k term test over the test by the test for divergence. And that's it. So we don't need the stuff up here. But if you wanted, if you wanted to go through and do that, you can, and then you could use a comparison test to prove that it diverges. But this is what I mean back up here when I'm saying, okay, in these standard ones, you get a p-series or geometric or a weird one. Well, okay, it's weird when the limit of the thing isn't 0. And so when you get over there, it's 125 over 16 to the k. That is geometric, so you could go with that. But the fact that 125 over 16 goes to infinity, 125 over 16 to the k goes to infinity, that means that it's going to diverge by the k term test. Does that make sense? Questions about that problem? Confused by the solution of the sheet. Yeah, so it sounds like what I did is I put a solution using the limit comparison because I wanted to show how to do it. But in this case, you don't need to do that. Does that make sense, Andrew? Sorry, it didn't make sense to me. Does that make everybody understand that? Whatever. Okay. And so then, okay, cool. Let's go back up. So we got number 11 on series 3. When you get the chance, can you do this series? Yes. Okay. Alex is the person who typed this in chat. Alex, let me see if this is what you mean, because you're typing it sideways. I think this is what you're saying. -1 to the n. I think actually it's like this. n-1 e to the 7 over n. Is that right?
Yeah, that's right.
Okay. So then this is again a weird problem because it doesn't kind of fit the mold of everything else. But if you look at e to the 7 over n as a sequence, what happens to 7 over n as n goes to infinity? You guys know? So 7
Is
over
it approaching like e to the 0? Is that
Yeah.
what we're going for? Okay.
it is. It's approaching e to the 0, but what is e to the 0?
1.
1. And so because that's not 0, then this is again a k-term test problem, or maybe we call it n-term test here. So what I would say is, okay, the limit as n goes to infinity of the absolute value of an is the limit as n goes to infinity of e to the 7 over n, which is e to the 0, which is 1. That's not 0, so the series diverges by the k-term test. Or maybe we'll call it n-term test, but same idea. Or test for divergence. Does that make sense? It's tricky because it's not clear that that's what you should do, but you have to notice the sequence is not going to 0.
Yeah, that makes sense.
Okay.
Do you think that we should always check k-term
Yeah.
test if we're like struggling?
Especially if it's weird.
Okay.
Like
Yeah.
for the vast majority of problems, the sequence is gonna go to 0. You know what I mean? So
Yeah.
because if not, they automatically diverge. But I'm sure you'll have some mixed in. I mean, if I'm writing a test, you're gonna for sure have one mixed in that is k-term test, and you need to notice that. So this one, I probably would not have checked to start out. I would probably have said, okay, compare to 125 over 16, and then notice, like what I talked to you guys through. But like back up here, like, okay, that's between 1 and -1. Well, this is huge. So, okay, that does go to 0. These go to 0, right? So like k over k to the 5 halves and k over k to the 3 halves and 1 over square root of k, those all go to 0. K squared over k to the 5th goes to 0. But you know what? If I change it and it's k to the 5th over k to the 5th, now it's k-term test. And that's what I mean by the weird example. Does that make sense?
Yeah, I get it.
Yeah, no, completely fine. Does everybody follow that? Okay. All right, cool. So let's go
Is
back.
there like a dead giveaway to like do the k-term test? Like you keep saying like if they look weird, is there like something that should just like give it away that is so weird?
This doesn't look like most of the series you're doing. You know what I mean? So is there a dead giveaway? No, there's not. But it's something you always can think about. So like that, if it's something where you can quickly look and say, okay, what's the limit as n goes to infinity, or what's the limit as k goes to infinity? If you can quickly figure out that's not 0, then that's what you should do, like automatically. And so like the other guy was asking, I forget who that was, but he was asking, should we always check that? Yeah, you should. Should you write out a 6-line limit? No, but you should glance at it and say, okay, can I prove that this limit's not 0? Well, in this case, yes. So yeah, you should always kind of check that in the back of your head.
Okay, thank you.
Yeah, no problem. Okay. Let's see, alternating series test. Colin, we did that, I think. And then will this record? Okay. Okay, I think I got probably number 20 on the test that I had shared. Okay, so let's go to that one. Oh yeah, okay. So so number 20 is the one that he was asking about. So the k-term test says that if the sequence does not go to 0, then the series diverges. Right? So if the limit of the sequence is not 0, then the series diverges. So now think about the equivalent of that. If the series converges, so also because of that, then the sequence must go to 0. Because if it didn't, then the series would have diverged. Does that logic make sense? This, what I'm saying also, that's equivalent to the K-term test. Logically, it's equivalent. So the K-term test says if the sequence does not go to 0, then the series must diverge. But that means if the series converges, if the series does not diverge, then the sequence has to go to 0, because if it did not, then the series would have diverged. So here they're telling you the series goes to 1.001, and it doesn't matter that that's bigger than 1. It doesn't matter that it's positive. It matters that it's a number. This tells you the series converges. Well, then the sequence converges to 0, because if it did not, the series would have diverged. Does that make sense to the person who asked it in chat? Okay. Does that make sense to everybody?
So wait, it's just saying the sequence is not equal to 0, so it then converges to 0?
No, this is telling you, so, okay, so you always have a sequence and a series, right? So like the sequence is the thing inside of the series, and then you've got the series itself. So what the K-term test says is that if the sequence does not converge to 0, then the series diverges. So if the sequence doesn't go to 0, then the series diverges. But just like that, kind of it's called the contrapositive, but kind of like the opposite statement of that is that if the series then converges, then the sequence does converge to 0. Because if it didn't, if the sequence did not converge to 0, then the series would have diverged. Well, this is the series. This is the sequence. So this is telling you the series converges. Well, that means that the series doesn't diverge. So this part had to be false. The series has to converge to 0 because the sequence has to converge to 0 because the series converged at all. I know that's weird. Does that make sense?
Yeah, that makes sense.
Okay. And so like on 22, it's telling you, okay, the sequence goes to 1. Well, that means it doesn't converge to 0. So then the series diverges. On number 21, it tells you the series diverges. Well, okay, then we don't know whether the sequence converges or diverges, because it could, like 1 over k would converge to 0, but the sum of 1 over k diverges. But then it doesn't have to. You could have a K-term test one where this converges to something else and this still diverges. And so we don't know. And so like the directions on this part were, if there's enough information, provide the answer. Otherwise, write not enough information. Okay, so a couple sequence problems. Yes. Let's do that next. And then integration by parts. If we have time, we will do that. But no time. All right, let me erase these because I was working these yesterday with people. But here's some sequence problems on this practice exam. So determine whether each sequence series converges or diverges. If the sequence converges or series converges, find its limit or sum. Right on the answers. Okay. So all right, so number one is a sequence problem where we're just trying to figure out whether it converges or diverges. And remember, we're not talking about a series here, so we're just doing the sequence. So we're going to pick out the biggest thing on top, biggest thing on bottom. So we pick 3 to the 4n minus 1 because we think of it as 3 to the 4th, so 81, versus 2 to the 5th, so 32. So 81 bigger than 32, so we pick the 81. And then we've got 10 to the 1st and 9 squared. 9 squared is 81, so we pick 9 to the 2n plus 1. Well, that's 3 to the negative 1 times 3 to the 4n over 9 to the 1st times 9 to the 2n. That's 1 over 3 times 9 times 81 over 81 to the n. That goes to 1 over 27 because if you have the actual number 1 to the infinity, that's 1. If it's the form 1 to the infinity, it's indeterminate, but 1, like 1 times 1 times 1 forever is 1. So we get this converges to 1 over 27. And then when you have an alternating sequence, we would almost always look at the absolute value of the sequence. And figure out what that does. So the absolute value goes to 1/2. Now, if the absolute value goes to 0, then the original sequence goes to 0. If the absolute value goes to something else and it's alternating, then what that means is like when n is really big, if n is like 100 million, then okay, this part, the non-alternating part, if n is 100 million is basically 1/2. And negative 1 to the 100 million is positive 1. So you get positive 1 times 1/2. But if n is 1,000,001 or 100,000,001, then okay, this is still 1/2, but negative 1 to the 100,000,001 is negative 1. So it flips 1/2 to negative 1/2. So an diverges because it alternates 1/2 to negative 1/2. And so we would say diverge here. And then we're going to do one more, and man, we're over, so I'm going to have to run. But this last one, we're going to do the squeeze theorem. And so we've got negative 1 over the square root of n is less than cosine n over square root of n is less than 1 over the square root of n. We're going to show that both of those go to 0. So then cosine n over square root of n goes to 0 by the squeeze theorem. So converges to 0.